Welcome back to The Explainer. So, today we're diving into Series 3, Episode 14 of our journey through the foundations of general emergence mechanics. And we're tackling a surprisingly profound question. What exactly is a chemical bond? Now, the ordinary view you probably learned in school tells us that atoms connect by sharing or transferring electrons, right? But in GEM, well, we need to go a bit deeper. Last time we looked at chemical handedness as bias without forcing. Today, we're going to see bonds as curvature-distribution solutions. Think about it like this. A bond is not just some microscopic link tying things together. It's actually a local solution to a coherence problem. When atoms get close to one another, their phase structures start to overlap. If that overlap creates a huge gradient cost, the atoms just repel, scatter, or just completely fail to bind. But if that overlap allows the phase curvature to be distributed smoothly, well, then a bond becomes admissible. There's this great quote that hits the nail on the head. A bond is not a rope, it is a negotiated geometry. Okay, so here's our roadmap for today. First, we'll go beyond the chemical rope. Then we'll look at the equation of connection, move on to molecules as curvature networks, and explore strain as strain debt. Finally, we'll wrap up with reactions and guided rerouting and tie it all together with chirality and coherence.
All right, Section 1, Beyond the Chemical Ropes. Let's really look at what happens when two atoms actually approach each other.
I absolutely love how this anchors the standard chemistry we all know into the deeper persistence mechanics of GEM. Let's do a quick translation. What we normally call orbital overlap, in GEM, that's coherence compatibility. Bond energy becomes persistence cost. That classic bond angle is really curvature routing geometry. When we talk about bond vibration, we're actually talking about relaxation around an admissible basin. And bond breaking? That's literally just the loss of a sustainable curvature path. It completely changes how you visualize it, doesn't it?
Moving right along to Section 2, the equation of connection. Now that we have the vocabulary down, let's actually see how a single bond operates mathematically.
So, here is the schematic cost of a single bond. This equation right here is the actual mechanics behind that negotiated geometry we just talked about. The variable S bond is defining the persistence cost of a connection between two centers. Let's break this down real quick, because bonding isn't just about physical proximity. It's all about these phase geometric relations. Theta 1 and theta 2, those are the local phase states. Lambda is the stiffness of the bond channel, and phi is the preferred geometric offset. To put that into perspective, imagine two whirlpools merging. If the difference between their phase states happens to match their preferred offset, they just spin together smoothly, right? The cost drops. But if they deviate sharply, the cost spikes, and the bond simply destabilizes. Okay, Section 3, Molecules as Curvature Networks. Let's expand our scope, because, chemistry rarely stops at just two atoms. If we take those individual connection costs and sum them up across an entire molecule, we uncover a pretty profound truth. Expanding on our last equation, this shows us that a molecule is only going to persist if the entire network graph can satisfy its phase relations without running into excessive frustration. Think of it like a giant dynamic puzzle. Every single atom or a local group brings its own phase state to the table. Each bond contributes a certain stiffness, and every preferred offset carries geometric information. Now, two atoms might be perfectly happy connecting on their own in isolation, but you put them into a larger structure, and suddenly their connection might create way too much global tension. So while a local bond might look totally fine, admissible, the entire molecule absolutely has to be globally admissible to actually survive. Which brings us to Section 4, Strain as Stored Debt. What happens when that global network has loops or constraints that cause conflict? Well, if the phase around a closed loop creates an unavoidable mismatch, meaning the sum of the preferred geometric offsets just cannot be distributed smoothly, the molecule is forced to carry a much heavier persistence cost just to remain itself. In standard chemistry, we see this show up as torsion, physical instability, or we might just say the molecule is highly reactive. I want to pause on this maxim right here because it's brilliant. Strain is stored curvature debt. Strained molecules aren't impossible. They don't break the rules. They just pay a much, much higher energetic price to maintain their form. It's kind of like a coiled spring. They're carrying around this stored curvature cost, basically just waiting for any excuse to break a bond and offload that coherence debt. All right, Section 5, Reactions and Guided Rerouting. Now let's set this entire network into motion and look at chemical reactions.
See, a chemical reaction is not just a bunch of atoms randomly swapping partners. It is literally the shells searching for a lower-cost curvature routing. It's trying to find a better route through phase space. The reactants are one admissible arrangement, and the products are another. But to get from A to B, the system has to cross a transition state. That state is a high-cost bridge. And that activation energy we always talk about? That's simply the toll it has to pay, the temporary spike in coherence cost, just to pass over that bridge.
And this is exactly where catalysts come into play. A catalyst doesn't force a reaction to happen. Actually, scratch that. It's more like it acts as a highly refined curvature guide. It essentially builds a lower-cost route, like a smoother, freshly paved road through the coherence landscape, allowing the old routes to relax and the new ones to form without forcing the system to climb that massive activation energy mountain.
And finally, Section 6, Chirality and Coherence. Let's tie this perfectly back to our previous explainer on chemical handedness.
So, in the traditional view, we think of a chiral enzyme as a lock and key. The wrong-handed molecule just physically doesn't fit the lock. But the GEM view, oh, it's so much more elegant. The enzyme presents a very specific phase geometric channel. One hand can route its curvature smoothly through that channel. The wrong hand, which by the way might exist perfectly fine on its own, simply cannot route its phase curvature through that available channel without paying an absolutely excessive coherence cost. It's all about geometric debt, not just physical fit.
To sum up everything we've covered in today's explainer, a bond persists because the participating atoms find a shared coherence path. A molecule persists because its network of bonds can distribute curvature without a runaway cost. Ultimately, chemistry itself is the study of which curvature-sharing arrangements can remain admissible.
I'm going to leave you with this provocative thought to ponder until our next explainer. Do atoms bond because they are pulled together by invisible forces, or because their curvature can be routed without tearing coherence? Thanks for joining me, and I'll see you next time.